Welcome to Ms. Johnson's Super Bowl recap. I'm Tyler Manning.
And I'm Barrett Johnson. Today we are discussing how physics was involved in the 2013 Super Bowl, which included the Baltimore Ravens and the San Francisco 49ers. The first clip of the game will analyze the Jacoby Jones kickoff return by using various measurements. The units we will be using will be yards and seconds.
As you can see, Jones is able to run more than the total distance from end zone to end zone, a distance of 108 yards and a total time of 15.2 seconds.
From these two measurements, we were able to determine Jones' average velocity throughout his kickoff return. We used the formula final position minus the initial position divided by the total time elapsed. So break out your calculators and perform this measurement. 108 yards divided by 15.2 seconds. The average velocity of Jones equals 7.1 yards per second.
After we performed this measurement, we realized that our answers are not entirely certain. Therefore, we wanted to perform a measurement of estimated uncertainty from the measured time. From physics class, we took the 0.5 lag time that Ms. Johnson said was associated with a stopwatch and divided it by the total time. The answer we got was 0.033, using only two significant figures, and multiplied it by 100, which equals 3.3%.
Next, we want to determine the acceleration of Jones as he returned the football. We use the formula distance equals the initial velocity multiplied by time plus half the quantity of acceleration, multiplied by time squared. Since Jones started from rest, the initial velocity equals 0. Therefore, in order to determine Jones' acceleration, we plugged in the various measurements. Distance equals initial velocity times time plus 0.5 times acceleration times time squared, which translates into 108 yards equals 0 yards per second times 15.2 seconds plus 0.5 times acceleration times 15.2 yards per second squared. So the acceleration is equal to the square root of 108 yards divided by 30.4 yards per second, which is 1.8 yards per second. Finally, we looked at the kickoff itself and its association with projectile motion. Projectile motion of the ball refers to the parabolic path that the ball travels after the kicker sends the ball in outfield. After the ball's peak, we wanted to determine the height that the ball reaches before falling into the outstretched hands of Jacoby Jones. Since we have not covered the effects of air resistance, we left that out in our calculations.
To identify this height, we estimated the initial velocity that the kicker kicked the ball, 30 yards per second. From this point, we had to determine the vertical velocity components of the ball's flight. We did this by multiplying the velocity by the sine of 30 degrees. Our estimated angle of the ball was struck. Therefore, we got a vertical velocity of 15 yards per second. We used the acceleration due to gravity of this ball in yards. We converted 9.8 meters per second to 10.7 yards per second. The time elapsed 1.4 seconds from kick to peak. The mass of a standard football is around 14 to 15 ounces.
After Tyler found the vertical velocity, our next step was to find the height itself. So we used the formula height equals vertical velocity multiplied by time traveled minus the 0.5 times 10.7 yards per second times time traveled squared. From our calculations, we got a measured height of 31.5 yards.
As you can see, football is much harder to watch when you're looking at it through terms of physics. SportsCenter has the narrators who look good in front of the camera, minus Stuart Scott, while Ms. Johnson's Super Bowl recap anchors have to know some scientific facts.
Thank you for your time. If you want to see more newscasts by me, I'll be in Raleigh next year.